It's my pleasure to introduce to you my PhD supervisor, Professor Sabah Jassim at the University of Buckingham. He's going to talk about the topological analysis of convolutional neural network layers for image analysis. Yeah, stage 2, Sabah.
Okay, thank you, Aras, and thanks to all for attending. Thanks, Aras, for bringing me to this subject anyway, when I was supervising you. I'm grateful to the previous two speakers because they covered the background to many of the slides. I'm going to go quickly because I've got so many slides. So I'll be talking about basically the topological analysis of convolution layers for image analysis. What happens in these layers? I will introduce a bit on the conventional machine learning and deep learning and pros and cons of the CNN, known ones anyway, and the ones that we are interested in, and then texture image landmarks and their persistent homology. And then I'll mention a few works, existing works on the relationship between topologies, using topologies for understanding the features and the weights learning by CNN models. I will then, this is the main fact, is the impact of these convolutional filters on the pH features of convolved images. Okay, and then we present experimental results for two diverse case studies, one from Aras's work and one from Jihan's work, and then I'll end up with the conclusions. Well, everybody knows by now that machine learning simply you aim to learn patterns in data for certain tasks, clustering, detection, segmentation, classification, and so on. Usually you use a modestly large set of samples of images, let's say, and you just extract features or parameters that model the objects you are interested in. And then automatically extracted ones features are more preferable. You train a classifier on these features, and there are so many of them, KNN, SVM, artificial neural networks, and so on. Deep learning, on the other hand, has the same objectives as conventional machine learning, but it learns a kind of ultimate feature map using several convolutional layers. And then the training uses multi-layered, also advanced neural networks, the fully connected ones. The layers meant to imitate the way the human brain in feature identification processing in a series of stages. So the illustration down there shows a diagram of two-layered convolution, two convolution layers plus the two fully connected ones. And the structure of convolution layers mostly consist of a number of operations, which normally leads to a kind of smoothing of the images they have, and also a kind of downsampling in some ways, until you get to a stage where the feature map is reasonably small. In many cases, it is in thousands anyway. So you then build the neural networks, fully connected layers of neural networks to classify. Pros and cons of deep learning, or CNN in general, pretty good performance, speech recognition, image classification, reduces the need for advanced searching. In the conventional machine learning, you need to know what you're looking for, in a way, what kind of texture analysis you want to do. And also there are too many of these architectures available, so these are the good things. The slightly less advantageous ones are the fact that the optimal performance requires a large amount of training data, although sometimes you could use various techniques to augment the data set. Computational slightly expensive, is not really a serious problem. The most serious problem is actually the fact that its decision-making is a black box with no explanation, and plus the overfitting of decisions to the training data set. And this is a source of adversarial attacks. Examples of the various models and architectures, there's so many of them. They only differ in the mostly they differ in the convolution, number of convolution layer, filter sizes, numbers of filters, and some kind of the activation function and the number of neural network, fully connected neural networks, and so on. And these are some examples, AlexNet. There are versions of these things, and there are even ways of generating these using some kind of optimization problem. I think there's a system called ENAS or NAS and ENAS, which try to find you an optimal CNN. The choice depends normally for you or anybody. It depends on many factors, including the image size that you are allowed to use and the volume of image data samples. Of course, the image size is a problem sometimes for medical things, because if you are taking scans of tumors, then this could come in any size, and that could be a problem. How do you actually enlarge it or make it small to fit the sizes required here? TensorFlow, transfer learning could help when there is a lack of samples, and of course data augmentation is used. There are many people who worked on, and I think the previous speakers have shown many of these, some of the works that one could have put here as well on these areas. But what is useful for us is that topological persistence is being used to improve image classification. This is one example. And another is they try to actually determine the nature of length features or weights by various CNNs. And for example, it was shown that the convolution weights, layers weight at depth 1 to 13, I think it is on a BGG network, only learns simple global structures. Some work on understanding the complexity, or measuring the complexity of the fully connected neural network by using what is known as neural persistent, and also recently differentiable topology layer has been introduced to compute pH on either level set, intensity level set, or distance-based filtrations, and with application to many other applications. The focus is in most existing people, most people, I think probably more the first speaker, Peter, has talked about some medical, biomedical imaging, which is very interesting. But there are very little on actually work in relation to these. So this is where we focused on. So this is simple. How do you do persistent homology? I think I'll skip this one quickly because this is being explained by the previous two speakers. We're not going to, this is another example of a situation where, just illustration of how do you build these given a point cloud. Here, the question is that, okay, how do I represent the image? Of course, there is the usual way most people do, which is by intensity level and increasing as one of the questions came about using thresholds, for example, because we know that pixels of any fixed intensity level, like this one here, for example, this image, if you look at it, you can turn it into a surface by adding the things. And these, at each intensity level, you could see, if you cut it, you can see that each level has its own geometry, topology or spatial distribution. So that's fine, but it is somehow, I think, inefficient for many applications, especially if you have the image size is large, unless you have lots of computational power. Alternatively, we are, and this has started with the work of Aras, that we can actually take any set of texture-related landmarks, discrete set of landmarks, can be made into a TDA representation of the image. And this is somehow, you might ask, which kind of texture-based feature landmarks you're talking about? Well, as we have already seen, and I think it was Henry who showed that earlier work on significant 3x3 image patches are known to map onto the surface of a Klein bottle, and there are also these other, some subsets of these are actually appear on the three-circle topology. So a variety of texture features in the spatial domain have been, on the other hand, in non-deep learning, a variety of texture and structural features in spatial domain, frequency domain, and transform domain have been investigated to do artificial intelligence-based image analysis. And for us, we think that landmark pixels whose 3x3 neighbors have some kind of structure associated probably with texture like LBP, local binary patterns, GLCM, HOG, and various other features in any domain can actually be used to represent or produce a topology. In other words, what I'm saying that actually we could have millions for large images, millions of different topologies. How do they interact with each other? This is a little bit one of the main difficulties. So if I take examples of landmark, we use few, but let me just introduce for a quick way is the so-called uniform local binary patterns in an image. Well, these are very easy to there is the LBP transform, basically takes any pixel and it changes its value in terms of its order relationships with its 8 neighbors. I mean, you could actually have 4 neighbors, 16 neighbors, and whatever, but this one is the simplest one. So simply you look at any pixel and you say, okay, look at the 8 and start from any point. Top left corner is as good as any other place to start with. And you go either clockwise or anti-clockwise, there's no difference. So you can then turn that into another byte, because each, if you think of one. So here you have 8 is bigger than 7. So you can see that therefore we put 1 here and then 10 is bigger and the rest are here are smaller. So this can be represented like a ring with 3 a circular binary string with 3 ones on it and the rest are zeros. The most interesting ones are the binary strings that have 1 run of ones, i.e. 2 transitions between 0 and 1 when you look at it as a circular string. So there are 7 such groups. Each one is identified by the number of ones. And we can just take each one of these, build a topology around it, and we can also use another one, which was, I think, we got it from other people using superpixels, whereby we look at the pixels where the surrounding 8 are all of the same These are we call the super pixel, 8 NSP. So we use all these things, but we are going to focus on the person ULDPs. And there are many, many other ways of picking up these things. Now, we come back to the convolution filters. How do we understand the actions of convolution filters, and especially if we are interested in the overfitting? The overfitting and the instability of the action could come from condition numbers. We can calculate the condition number. This is a formula. Many of you would have used it anyway. And just to show, illustrate its link to the overfitting is that when you look at this ill-conditioned filters, normally they are either singular or quite close to being singular. And you can see in this example, you have two images of tumors. Sorry, it's one image. The top one is an image of a tumor. The next one is simply the same one with a bit of noise. And you can see some of the filters may have the same, extract similar features, but some will extract actually different features. And this is where then you could see, obviously, that the homology or the persistent homology of these features, we can pick up those, some of these, could distinguish it from the other one. Therefore, this is the problem with the overfitting. Here we take the, on the other hand, a filter could also have an impact on the entropy in the image. When you apply it to an image, the question is what is happening to the information in the image? Do you lose the information or not? There are various ones. We always said those filters that keep the entropy high or as before or slightly more or less, then fine, these are good ones. The medium ones are the ones which loses some, but they still have some, but the bad ones are these low filters. When we actually try to find the distribution of condition numbers for a large number of filters, Gaussian filters initialized one, we found that, well, they are reasonable good condition numbers. They have majority of them. But of course, we then applied those on the pre-trained, which are coming from the ImageNet. And you could see that they actually, the process of training, whether you are doing the training or the natural, or even through the transfer learning when we use it on ultrasound bladder images, the condition numbers get worse. And also there will be a loss, great loss of, some of them lose a lot of entropy. So this shows that actually convolution layers will result in increased instability and also reduce entropy. Well, so what is good about them? Well, let's see what would be the impact on decision making. So to do that, then we used persistent homology. We took these landmarks on the original image and on every stage of the convolutions for each convolution layer, and see what is happening if we are just classifying it as if we are doing the usual classification with SVM. We applied this for both two applications. It's the morphing. I think Aras is going to talk about this later on, maybe in more details, but simply you are taking two images, one genuine, well, both are genuine actually, but one of them maybe for a person who is entitled to have a passport, the other is not entitled, and then they morph them in such a way you can get another image, and that image can actually be used to create a passport for the second person, which could apparently tend out that it could actually, if the morphing is done well, it could go passing the machine verification as well as any trained border agency. And I think last week, I think Aras was also in one of these webinars. We heard that among the people that they were saying, these are the border security people they're talking about. At least they know there are thousands of these being detected already. So Aras worked on these, take landmarks, build the persistent homology for genuine and for morphed ones, and try to build a tool to detect these things. Well, the point is that morphing is actually result in invisible changes. That's why nobody could actually detect it with naked eye or even some expert ones. So he built the pH models for these things and turned it into a detector, morph detector. Well, this is just a simple illustration of what happens when you have these different ones. You could see that there are some, at some stages, these will be different from the others, the genuine from the morphed ones. And we did some experiment on a specific database, which is not necessarily the best database, but it's fine. And one of the techniques known as complete morphing. And others found very good results. In fact, they were almost 98, 97% accuracy. Now, we took them through the convolution layers. And these are the results. What do we see here? That at each stage, there are all these different actions. The first two layers have, and the last layer have max pooling, but the middle ones do not have the third and fourth. And when you look at these things, you will find that for all of the groups, roughly speaking, they perform similar accuracy. So the convolutions did not deteriorate. Sometimes it improved, at least in layer one, sometimes it improved, but these are marginal. So for all ULBP landmark groups, the performance of the pH-based morph detector improves, albeit very marginally, during layer one. Except for the max pooling of layer 5, somehow the performance
Sabah?
of the other, sorry.
Just to let you know that you are out of time, I'm going to give you a couple of more minutes. You're already 3 minutes behind the schedule. Yeah, just
3 minutes is fine. Yeah, okay, that's fine. Okay.
Yeah.
Second case study is basically the ultrasound. I think it's not the liver. Sorry, these are livers, but we are talking about the bladder. I'm sorry, this is a cut and paste issue. And when we did the same thing with these, we found that in this case, the pH in the original image was actually not performing any good because they were almost equivalent to a random decision. However, the convolution filters actually improved to the point of getting to around 75, 76, especially at the first two layers, whether in dimension 0 and also in dimension 1, as I'll show you next one. But so there is an improvement here. And incidentally, the transfer learning, if we don't, we are trying to peep into how it is working. The final results of the transfer learning actually do not get more than 75%, even though we have, at each one of them, we can get to that level at some stage. This is the dimension 1. And if we analyze this, we could see that smoothing effects of convolution filters is not all negative. The performance of the pH tumor diagnostic scheme improved significantly by the various operation of the first two convolution layers. These gains, unfortunately, lost. I didn't show the other layers, but they are lost later on. Filter smoothing, this is an interesting observation we find, that filter smoothing affects many effects may help actually discriminating properties of certain texture features. In fact, many of the ULBPs, after the first convolution or second, they disappear in the case of benign tumors, which makes it easier to separate from the other. And using many convolution layers in the hope of extracting or learning better results, perhaps it's not necessarily a good one, and may even become a counter action. So there are the only thing I want to say, there are so many of these texture landmarks that we could use. So there are many of these. And then question is, how do we actually find these different ones, put them into a way of doing image analysis? The only thing is that for medical diagnosis, we need to test these hypotheses on different CNN architectures, tumor types, and other non-natural image modalities. And we may benefit from it. In the usual machine learning for pH, even for natural, I think we might even benefit by incorporating some convolution layers. And this is where I stop. These are the list of some of the references, and these are the two people who contributed to this work. One of them is Aras, and the other one is Jehan, who's done the work on the tumors, and she is doing more on these. Thank you very much for that.
Thank you very much, Sabah, for this interesting talk. Let's unmute yourself and just clap for Sabah. Thank you. I think we have a time for a very quick question because, well, maybe a couple of questions. Any questions? Let me check the chatting. I can't see any from my side. Henry, if anyone sends you texts or questions, please go ahead and ask. And I'm sure Sabah will stay here for the virtual coffee break. If you have questions, feel free to ask Sabah, because after Vitaly's talk, we have 40 minutes virtual coffee break. Yeah. Okay.
I have a question.
Yeah, go ahead.
Okay. So you talked about neural persistence, the persistence work that you briefly mentioned, I believe.
This is a work of a paper, one of the references in the list of references I gave.
Yeah. So can you talk a little bit about what do you expect to get from that calculation of persistence?
Well, I think, well, I haven't read it in more details, but all I can see that they claim that knowing these things could help you design a more efficient neural networks. A lot of things you can actually, I think it is used for not filtering out, what you call them.
Yeah, they call it filtering.
Removing some weights. Okay? Mm-hmm. So basically the weights are used, not only the weights, but the connections together to build this persistent homology. They call it neural persistence, sorry.
Okay.
I'm not sure, but the references in the list of references I gave.
Yes. Thank you.
I think I could tell you which one later on. Yes.
Thank you. Yeah. Okay. Thank you. Thank you very much. Thank you, Sabah, again. I'm sure we can continue this discussion in the virtual coffee break.